Okay, so let's get back to our class. So we have finished basically the parts for integer multiplication and matrix multiplication. So we have been talking about divide and conquer algorithm for quite a long time. So we will talk about the last example that we are going to explain in this class for divide and conquer algorithm, fast Fourier transform. So basically, this is the last class of algorithm based on divide and conquer that we will introduce in this class. We will talk about this for an hour or maybe an hour or two. So basically, something like that. And actually, we will move on to the next kinds of algorithm design ideas. So what is fast Fourier transform? In general, for Fourier transform, this is just something very useful in general. So it actually has wide applications in, you can imagine in telecommunications, basically in your cell phones, for instance, in telecommunications, and also signal processing, control systems. Basically, for instance, like image processing. Maybe, for instance, like speech recognition. And also, for instance, in quantum physics. So actually, in our homework assignment, assignment 3, we will have a problem to see how Fourier transform is helpful in physics domains, etc. Okay, so this is still a bit weak to talk about. So let's talk about something that is concrete. So let's talk about polynomials. Okay, so for polynomials, there are different ways to represent a polynomial. But I think the most naturally, as we have been always talking about, is coefficient representation. So what do I mean by that? So basically, you have like a polynomial, for instance, a of x equals to a0 plus a1 times x plus n2, a2 times x squared plus dot 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 plus a n minus 1 times x n minus x to the n minus 1. And also similar, maybe have another a polynomial, which is bx equals to b0 plus b1 times x plus b2 x squared x b of n minus 1 times x to the n minus 1. And the degree of both polynomials are actually n minus 1. So we consider some, computation problems among like polynomials. So in general, for instance, we can consider addition. If you have like a polynomial ax and bx, the cost of adding them, I guess this is just very straightforward. The cost is just O of n. So O of n arithmetic operations. So this is just because ax plus bx, equals to a0 plus b0 plus a0, a1 plus b1 times x. In general, it's just like you imagine that I tell you there is one polynomial A and another polynomial B, and I require you to return me the polynomial A plus B. If you have this kind of coefficient representation, this is just very straightforward. You just like, take the sum of all the coefficients. A0 plus B0, A1 plus B1, etc. This is just very straightforward. And I think another very important function in polynomials is evaluation. By evaluation, you just need to compute, input x. The input is now x, and I require you to output the value of ax. So what is the cost of evaluation? Yes. So the cost is actually still O of n here. But this is actually a little bit more sophisticated. So this is an idea called the Horner's method. Oh, sorry. Horner's method. So actually the idea is that, you just look at the very end of this, because you're actually multiplying x for n minus 1 times. You can consider, maybe you want to, for instance, consider like the very last two entries. they actually have something in common. That is basically you can consider this as like this. X to the. So basically this the above equals to the bottom one. So basically, I mean, for this higher power part, you can actually make like a recombination, and maybe basically for a minus one times x to the a minus two times x to the minus two plus this minus one term, you can just like recombine them to like this. But actually, this is something you can do like again and again. So in general, you can actually it's not very hard to examine that a of x it equals to a0 plus x times a1 plus x times a2 plus da da da. And finally is x an minus 2 plus x an minus 1. And there are a lot of brackets here. So in practice, you first compute this times an x plus a minus 3 times an x plus the next a times x plus the next a, etc. And it is clear, you can clearly see that basically this is still going to give you a linear cosmos. So any questions? I guess this should be relatively straightforward. So I guess let's move on to the next part. So the important thing, I mean, for this coefficient representation is that maybe the thing when we want to comply the multiplication for the multiply part. So, and I think typically, I mean, in this scenario, it is on the other hand also called convolve. This is probably going to be a little bit complicated because in this case, ax times bx. So just think about what this is going to be. So you have these two polynomials here. So this is now going to equal to the summation of I equals to 0. So because both polynomials has degree at most n minus 1, the final output should be of degree at most 2n minus 2. And this equals to a summation from I equals to 0 to 2n minus 2 of ci times x to the I, where ci equals to a summation of I of j from 0 to I, aj times b, I minus j. So I guess this should be relatively straightforward. So questions. Okay, so if you just consider this, I mean, you consider such kind of multiplication. So in the worst case, cos of this is going to be n squared. This is because you have 2n minus 2, basically On coefficients. And basically for the CIs here, so especially for the C's in the middle, I mean, for instance, around Cn, there are actually On terms inside. So in the worst case, I mean, the cost of just doing this in a brute force way is going to be On squared. Let me actually also mention this in brute force. Okay, so this is, I mean, like a bottleneck for the coefficient representation. So we clearly see that in general for addition and basically for evaluation, I mean, polynomials, coefficient representation can finish this very efficiently. But for multiplication, this is like a bottleneck, and hopefully this is something we can further improve here. So before we actually delve into that, I think we need an important result among polynomials, which is actually have like a very significant name called a fundamental theorem of algebra. Oh, excuse me. And this is actually originally proposed by Gauss. And this is, on the other hand, also known as the Gauss theorem. So what is the fact? The fact is that a degree n polynomial with complex coefficients has n complex roots. So as long as you have like n degree polynomial, and actually we have complex coefficients, the number of roots is exactly n here. So this is not something we are going to prove because this is a little bit advanced. But in general, I mean, the point is just like after we have this, we take this as granted, and we think about what is the properties that we are going to have. I mean, when we want to consider good algorithm for like polynomial multiplications, etc. So this is really like a fundamental theorem. I mean, if you're interested, you can just check a standard book in complex analysis. So this is something very standard. And I think a direct corollary that we can make a discussion here is that if we consider a degree a -1 polynomial, maybe let's call this like AX, it is actually uniquely specified by its evaluation at n distinct values of x. Okay, so what do we mean by that? So we consider a direct proof here. So suppose AX and A prime x both evaluate the same. Or at n distinct values. Distinct values of x. So because we are talking about degree n-1 polynomials, and I think here we are actually assuming that both the degree of both polynomials, they're actually at most n-1. Then we know that actually the degree of the polynomial n minus a prime is actually still smaller than n-1. Because on the other hand, you look at addition here. I mean, addition, subtraction, in general, they don't increase the degree of the polynomials. So the degree of a minus a prime, it is still at most n-1. And actually, so because we're talking about a case where a and a prime x, they have a value, the same value at n distinct values of x. So this is actually suggesting that a minus a prime, it actually has at least n complex roots. And this must suggest that a and a prime is identical to 0. Otherwise, because if it is not identical to 0, it is a polynomial of degree at most n-1, but it actually has at least n complex roots. It's just like get a contradiction to the Gauss theorem. Actually, this suggests that we must have a prime equals 2. So any questions for this corollary? Okay, I guess this should be relatively straightforward. So if any questions, just feel free to ask. Okay, so this is basically about a very basic result about how we are actually going to determine a specific polynomial. I mean, if we know that a specific polynomial has degree at most n-1, then basically it suffices that we have evaluation. I mean, we have the function evaluation endpoints, and then basically we pin down this corresponding polynomial. So this also suggests us to consider, I mean, some other like way to represent a polynomial. So maybe not only the coefficient representation, but maybe we can also represent a polynomial using its function evaluations. So this is basically suggesting polynomials. So we can consider such kind of point value representation. So what do I mean by that? So basically, you know that if you have a polynomial A, where basically the degree of A is smaller than n-1, you can actually represent this A by a group of points like x0, y0 until xn minus 1, yn minus 1, where basically axi equals to yi, any I equals to. For any I belongs to 0, 1 until n minus 1. And similarly for bx, you can store this as like x0 z0 until x n minus 1, c n minus 1. Okay, so basically for this kind of point value representation, in this case, you consider addition. For addition here, basically you have the cause is CO of n arithmetic operations. Because I guess if you store, according to this point value representations, doing addition is also very straightforward because then you will have x0, y0 plus z0, x1, y1 plus z1, etc. So basically for this point value representation, so addition is actually not a big problem. So how about multiplication now? So what is the cost of multiplication for the point value representation? I guess in this case, similar to addition, because the main cost of multiplication, in coefficient representation is that you really need to take all these kind of summations. So this is actually a little bit problematic, but actually for multiplication here, in this kind of representation, it is relatively straightforward. You actually only need to, roughly speaking, of O of n points to calculate the multiplication, but we need to be a little bit careful because basically, if you consider multiplication of polynomials, its degree becomes at most 2n minus 2. So this is basically something we need to pin down here. We don't want to get something we got lose control here. So basically, we say that multiplication the cost is O of n, but we need 2n minus 1 points. So basically, in this case, basically for 2n minus 1 points, here it is, we need to be a little bit larger. So maybe originally the input here, we should have like a 2 in these places. But nevertheless, for the AX and BX, it can be completely pinned down by a group of vertices where you have like S0 and Y0 times Z0, X1 of Y1 times Z1, until x of 2n minus 1 with the corresponding function value of y 2n minus 1 times z2n minus 1. So basically, this is very straightforward in the multiplication form. Basically, for multiplication of the point value representation, this only takes linear cost. So the thing that is a little bit painful, this point value representation, compared to the coefficient representation, it definitely has some kind of trade-off. It is not, like one is always better than the other. So basically, we have been talking about addition, multiplication. So the remaining thing is about evaluation. So basically, how we want to evaluate the function values. Here it is good that we have stored already stored n evaluation values. But for instance, if here I give you like a totally different x, what is its corresponding function value fx? This is basically, I guess, the value of ax. Here we are using a and b here. What is the value of ax? So this is something a little bit complicated. Maybe you want to think about, here, if you have this kind of point value representation, what are you going to do to recover like another value of ax? So here, maybe we can consider like a form, for instance, like this. So we consider ax equals to the summation of k equals to 0 from k equals to 0 to n minus 1 with the value of yk times this. So we consider a form like this. So why do we want to consider this? So just imagine for an arbitrary k here. What's the value of ax k? I guess you can see, I mean, here in general, I mean, there are a lot of different cases, but maybe for instance, assume here we have like a K prime here. I mean, if the K prime here is not equals to the K that we are currently interested in. So if you have like a K prime here, then actually basically for this term, you're actually going to get a cancellation because you only concern the case where y not equals to K prime. But if K prime not equals to K, you can actually take J here to be K. I mean, you actually got such kind of term, and actually this just cancels because it is not zero. You have this xj minus xj. But nevertheless, I mean, for this specific K here, I mean, you just consider this part. I mean, let me actually go this back. Yes. So if you just consider this specific term, I mean, the right K here, you actually put a K here. Then you can clearly see the numerator equals to the denominator, and actually basically this part just equals to 1. And of course, this is going to give you, I mean, this part equals to 1. All the other places, I mean, it is going to give you 0. And the 0 is going to kill the corresponding yk prime here. So this is suggesting that for arbitrary k here, I mean, from 0, 1 to n minus 1 here, the value of a of xk just equals to yk. And also on the other hand, the degree of a just equals to n minus 1. I think let me here's this. The degree of the polynomial a here just equals to n minus 1 because all of this, I mean, this is the part where you have this variable, this x here. I mean, there are n minus 1 terms for, I mean, for an arbitrary k here, there are n minus 1 terms in this this multiplication. And actually, addition of degree polynomials of degree n minus 1 is still going to give you a polynomial of degree n minus 1. So this is actually suggesting that the degree of a here equals to n minus 1. But furthermore, recall that we have this corollary here, this corollary based on Gauss theorem. That in general, degree n polynomial with complex, basically a degree n minus 1 polynomial is actually going to be uniquely specified by its evaluation and distinct values of x here. So here, for this polynomial, so basically for this ax we are considering here, we are actually, we have already specified n values here. I mean, axk equals to yk here. So this just suggests that this is the exact polynomial that we're actually interested in. Actually, this is the answer to the ax here. So this ax here, so basically this form, it has a known name in mathematics. This is called the Lagrange interpolation formula. I think not right here. So Lagrange interpolation formula. Oh. So this is something, I mean, very standard in terms of polynomials. And basically, we know that as long as we have evaluations at endpoints, basically we can pin down a corresponding minus 1, degree minus 1 polynomial using this kind of idea, basically using a Lagrange interpolation formula. But unfortunately, the cost of the Lagrange interpolation formula, you can clearly see that the cost is O(n) squared. Because basically you need to consider such kind of multiplication for all the k's. And basically for each k, this multiplication cost is O of n here, and you actually have the n choices of the value k here. So this is in general quite expensive in terms of the complexity. Okay, so is this discussion about point value representation clear to you? So do you have any questions? Okay, so if there is no confusion, let's make a very brief summary here. So we say that actually here there is a trade-off. So we want to actually have like fast evaluation or fast multiplication. So this is definitely a trade-off that we need to like have a better understanding. So here we have this, it's a brief table here. So we have representation we have actually the cost of multiply, and actually the cost of evaluate. So the good thing for both representations, for the coefficient and also for the point value, the addition takes ON cost. So this is the reason why we actually just omit the corresponding column for addition, because this is just very efficient. So for coefficient representation, the cost of multiply is ON squared, but evaluation can be done very efficiently. But also on the other hand, for the point value representation, the cost multiply is actually ON, but unfortunately the cost of evaluation is ON squared due to Lagrange interpolation formula. So we actually want to have a better trade-off here. In general, maybe I want to think about whether we can give like a good calculation for both the multiply and multiplication and also the evaluation here. So we mark our goal here. So key goal here is to make all operations. Maybe, for instance, we can ideally by efficiently converting between these two representations. Right. So what do I mean by that? So basically, I mean, for coefficients, we are going to have like a few values. I mean, like A0, A1, until maybe like A minus 1. And basically for a point value iteration, so basically we are going to have a bunch of different values, which is basically x0, y0, I mean x1, y1, until xn minus 1, yn minus 1. Hopefully we do want to consider like the transition between this is the coefficient representation. And also on the other hand, for point value representation. I mean, if we can efficiently do such kind of transition, I mean, hopefully the cost is not as bad as ON squared, then basically we are actually good, because for either the multiplication and also on the other hand for evaluation, we just make the transition and do the fast. So basically this becomes the main focus that now we are actually going to talk about. So any questions? Okay, so maybe for instance, let's first talk about coefficient. 2-point value. So in this part, because we have coefficients and we want to have point value representation. So basically now we are given a polynomial. A0 plus A1x plus A minus 1x minus 1. Want to evaluate it at n distinct points. 0x1, 2x minus. So basically, it is something like this. So we are always going to represent the function values by y's. So here we are basically like computing such kind of linear, basically a linear map. So here we are having A0, A1 until an minus 1. So actually to evaluate the function value, that is more like we are multiplying these matrices. So here we have like the 1 x0 and minus 1. So 1 x1 and minus 1. So here we have a 1 here, so we have x and minus 1 here, and here we have x and minus 1 to the minus 1. So just recall the coefficient value. So because we have this y0 equals to a0 plus a1x plus a1x0 plus plus a minus 1x0 and minus 1. I mean, this is just the way we understand this. And basically we have this multiply this is exactly basically this one. And similarly for the other rows, times this column of coefficients is 0, A1 to A minus 1. So basically, talking about coefficient to point value transitions. So it's just like in general, we have this input and we know what the x's are. It's just like we need to solve this matrix multiplication problem. I would say it's a matrix vector multiplication. So is this clear to you? I mean, here it is basically what we need to utilize, because I mean, in general, just imagine we have like a whatever a general matrix, and like because here the vector here there are input coefficients. This can be in general I mean, this can be in general arbitrary. I mean, we don't have like a control on that. But in general, it is only like a point value representation. We have our freedom to choose which points. I mean, basically which axis that we can use. And actually, this matrix, I mean, you see like this is really a very special kind of matrix. And I think this in general has a name called Vandermonde matrix. But I guess the name is not important. Nevertheless, the point is that it is basically like powers in the rows of the matrix. And basically we want to utilize such kind of structure. But nevertheless, I mean, if we are not clever enough, I mean, if we just do like brute force calculation, I mean, it's just like O(n) squared for brute force matrix vector product. Okay, so any question at this point? Good. Okay. So I guess we are talking about divide and conquer algorithm. So it is then very natural that, I mean, we have also been seeing that Karlsruhe's algorithm and also Strassen's algorithm. But here, I mean, as I just mentioned, the strategy is a little bit different, because here it is not, I mean, I directly give you two matrices or directly give you a matrix and vectors, and you just like, I ask you to multiply them. Here you have the freedom to choose this matrix to actually store a point value iteration, sorry, a value representation here. But actually, you have like a fixed vector here. So maybe here we need something slightly different from Karlsruhe's algorithm and also the Strassen's algorithm. I mean, it's not like slightly different, but actually a significant difference. Yeah. So how about we do this? I mean, the idea is still divide into two pieces. The hell? How do we want to do that? So one observation, I mean, this really sticks to what kind of problems that you want to make the division, basically use the divide and conquer algorithm. But for polynomials, I mean, maybe you have the following such kind of observations. So I mean, assume that you have like ax equals to like a0 plus a1x plus ax. Maybe let me write down some terms here. So assume that we have a degree 7 polynomial here. So one thing that maybe we can think about is that maybe we can rearrange the polynomial in terms of even and odd degrees. So what do I mean by that? For even degree, we just consider the degree of the monomials with even power. So basically, we have a0 plus a2 x squared plus a4 to times x to the 4 plus a6 times x to the 6. And also similarly for the odd terms, we can consider just like this. So the strategy here that we are actually, you can see the point is that we basically want to break the polynomial. Up the even and odd parts. So what is the benefit of doing this? So a significant benefit that we can see here is that what if we want to represent the value of AX by A even, A odd here? So we can clearly see that for A even here, so we can basically write something like, and actually, I mean, instead of writing all the powers like this, what if we consider these polynomials? I mean, this degree of A equals to 7. But on the other hand, actually degree of A even and A odd is actually 3. So basically we make a deduction on the degree of this A even, A odd. So we don't actually, we not only, we can have this a division in terms of the odd and the positive, odd and even powers, but we can also actually divide the corresponding power by a 2 here. And then in this case, we can write this. And write like this. So any questions? So this is like an initial idea. I mean, how we want to make a division. I mean, in terms of this kind of polynomial problems. So basically, we have this A even, A odd. And the next benefit is that maybe we can play a little because we have like x squared here. And basically, this x squared is in general something you really enjoyed in terms of variables. So a very natural thing that you're going to consider is like, what is A of minus x? So this can actually directly follow just by the definition. So minus x squared just equals to x squared. So this just directly follows. And for this part, the x is replaced by minus x. And actually also for A odd, x squared, I mean minus x squared always equals to x squared. So you also have this. So I guess this is relatively straightforward. So after having this kind of idea that you want to divide a polynomial, I mean, maybe like a general polynomial into like the even and odd parts. So here, I mean, we don't like brute forcefully cut this, I mean, into like high degree or low degrees. You can do that, but that just becomes the Karlsruhe's algorithm. So here we just want to utilize the structure of polynomials and we divide according to even and odd. So, I mean, also, as we just mentioned, we actually have the freedom to choose what is going to take place here. So basically the value of x is, so this is actually something we can feel free to choose. So from this very beginning example, like an intuition, we can do is that we can choose 2 points. To be +1 and -1. And actually, by doing that, we know that A1 actually equals to A even of 1 plus 1 times A odd. And actually, on the other hand, A of -1 equals to A even 1 minus 1 times A odd. So what is actually suggesting by this? So this is basically suggesting that we can evaluate polynomial of degree at most n at 2 points by evaluating 2 polynomials of degree smaller than over 2 and actually just 1 point. So for both A even, A odd, the suffices to know the value of ones. And actually, only knowing A even 1, A odd 1, we can get the value of A1, A minus 1. So this is really something quite interesting. And maybe, I mean, this is a good thing that we can utilize from this form of A even, A odd. And maybe the next thing is that we can further delve into this, and maybe we want to like further improve this and like get better understanding in general about like the polynomials A here. So is there any question here for, I mean, this kind of division of A even, A odd? Okay, so let's continue. So this is like a very first step, and maybe our next question is how do we continue this? So, I mean, we have the ones and the minus one here. So maybe one thing that you are going to play with now is further consider something for this x squared. So how about like the imaginary units? I mean, like I and minus I. So maybe we can consider something like this. So now we not only have this group. So let's actually just like copy this here, copy and paste it here. So what if we play with the imaginary units AI here? So just according to the definition, because I squared equals to minus one. So this actually equals to A even of minus one plus I times A odd of minus one. Because again, I squared equals to minus one. And similarly for A minus I, it also equals to A even minus one minus I times A odd. So basically, in general, we can actually just copy this sentence. So this is saying that we can evaluate polynomials of degree at most n at 4 points. But actually evaluating two polynomials of degree at most n over 2 at 2 points. The two points being like a even 1, a even minus 1. This is for a even, and also for a odd is also the function value at 1 minus 1. This is clear to you. Okay, so you clearly see that, I mean, here we are really utilizing the structure of even and odd, and here we move from like 1 to minus 1, and then we further consider that basically let's draw the complex plane. So originally we have 1 here, and then we have minus 1 here. I mean, actually now we also go to I and minus I here. So maybe the next thing that you want to consider is that maybe we want to further do this. I mean, in general, maybe we want to consider further like imaginary units on this basically unit imaginary points, and maybe hopefully these can be helpful for us. So this is just an intuition, I guess. Mathematically, I mean, to really work with imaginary points, we need a little bit further definition here. So let's actually make this idea more formal. So here we say that we have this kind of key idea that we can actually choose x to be omega to the k, where thus omega is principal nth root of unity. So this just means that omega equals to e to the 2 pi I over n. So recall that that actually an nth root of unity is actually a complex number such that basically its nth power equals to 1. And basically, you can clearly see that they are actually omega to the 0, omega to the 1, omega to the 0 actually just equals to 1. Omega to the 0, omega to the 1, until omega to the minus 1. So why is this the case? We just imagine that omega to the k to the n, it just equals to e to the 2 pi I. Because we are considering omega to the k, so here it is equals to e to the 2 pi I k over n, nth power. And actually this equals to e to the pi I with a 2k. So by Euler's formula, we know e to the pi I equals to minus 1. This is just Euler's formula. So this equals to -1 to the 2k, this equals to 1. So that is basically saying that all the nth root of unity is basically omega to the 0, omega to the 1, until omega to the -1. So is this clear to you? Okay, so here we have this notations for the nth root of unity. So similarly, we can consider, because we are considering like cases of smaller dimensions, so we consider instances of dimension n over 2. So basically, we can also consider like the n over 2th root of unity. So we denote them as like, I mean, we have used the omega here. Maybe let's, for instance, use the v here as v0 until b of n over 2 minus 1, where v equals to e to the 4 pi I over n. Because we are talking about n over 2th roots of unity. So basically, in this case, we know that omega squared equals to v. And actually, omega, I think I was writing omega here, so it's not w. And actually, omega squared to the kth power also equals to v to the k. Okay. So here, basically the matrix becomes something like this. So we have like this y0, y1 until this yn minus 1. So this is actually finally the matrix of this. So basically this, I'm actually just writing this again. But I think here I actually pin down what the axis that we are going to choose. The axis that we are going to choose is just the nth root of unity. So here it is actually all the ones. Now actually here we have 1 omega squared until omega n minus 1. And here, the next point we are going to choose is omega squared. Then it's actually omega squared. And they actually, we just take another look here. x1 squared, x1 cubed, etc. So here we have 1 omega squared, omega to the 4th, until omega to the 2 times n minus 1. We actually zoom in a little bit. So for the last line, there's going to be 1 omega to the n minus 1, omega to the 2 times n minus 1, until omega to the n minus 1 times n minus 1, omega n minus 1. And actually, we have this a0, a1, a minus 1. So this step, I mean, having an input of all these a0, a1 to n minus 1, we time this specific complex matrix. This is just called a discrete Fourier transform. Also known as DFT. And this part is called a Fourier matrix. Also denoted as Fn. So any questions at this point? Okay, so here we make a further notation. Basically, without loss of generality, we assume n is a power of 2. Otherwise, say 2 to the k smaller than 2 to the k minus plus 1. I mean, this is just like a normal trick that we have been doing. We can just feel free to take an equals to a of 2 to the k plus 1 minus 1 equals to 0, and run the DFT for 0, a1 until a2 to the k plus 1 minus 1. Just run this. So this is going to give us at most the overhead of the 2 here. And actually, you can just imagine it is like a polynomial of even larger degree, but all the further terms, they actually have 0 coefficients. Okay. So next, I mean, for the next hour, we're actually going to introduce how we actually use the divide and conquer to solve the DFT. Okay, let's take a break.